Good day everyone. I am Shana Tongkwa, your last reporter for this SEM. Today, we will discuss about the simplex-based sensitivity analysis. The contents of our topics is the sensitivity analysis with the simplex tableau. Under it, it's the objective function coefficients, right-hand side values, and the simultaneous changes. So first, let us define what is sensitivity analysis with the simplex tableau. So the usual sensitivity analysis for linear programs involves computing ranges for the objective functions coefficients and the right-hand side values, and as well as the dual prices. So, next slide. So the first one is the objective function coefficients. So sensitivity analysis for an objective function coefficient involves placing a range on the coefficient's value. We call this range the range of optimality. So as long as the actual value or the objective function coefficient is within the range of the optimality, the current basic feasible solution will remain optimal. So, the range of optimality for basic variable defines the objective function coefficient values for which that the variable will remain part of the current optimal basic feasible solution, while the range of optimality for non-basic variable defines the objective function coefficient values for which that variable will remain non-basic. So, in computing the range of optimality for an objective function coefficient, all other coefficients in the problem are assumed to remain at their original values. So, in other words, only one coefficient is allowed to change at a time. So, to illustrate the process of computing ranges for objective function coefficient, recall the high-tech industry introduced in chapter 17, which is the previous chapter. So, the linear program for this problem is restated as, that's it, 50x sub 1 plus 40x sub 2. So, 3x sub 1 plus 5x sub 2 is less than or equal to 150. That is our assembly time. And 1x sub 2 less than or equal 20 is the portable display. And x sub 1 plus 5x sub 2 is less than or equal 300 is the warehouse capacity. So x sub 1, x sub 2 is greater than or equal to 0, where our x sub 1 is the number of units of the desk pro, and x sub 2 is the number of units of the oh, excuse me, of the portable. Sorry for that. So, this is the final simplex tableau for the high-tech problem as follows. So, that is our table. So, recall that when the simplex method is used to solve a linear program of an optimal solution is recognized when all the entries in the net evaluation row C sub j less the z sub j are less than or equal to 0, because the preceding simplex tableau satisfies this criterion. So, the solution shown is optimal. However, if a change in one of the objective function coefficients were to cause one or more of the c sub j less c sub j values to become positive, so then the current solution would no longer be optimal. In such case, one or more additional simplex iterations would be necessary to find the new optimal solution. So, the range of optimality for an objective function coefficient determined by the coefficient that maintain for all the values of j. So here, let's illustrate this approach by computing the range of the optimality for C sub 1, the profit contribution per unit of the desk pro. So using C sub 1 instead of 50. So as the objective function coefficient of x sub 1, the final simplex tableau is as follows. So that is our table. So note that this tableau is the same as the previous optimal tableau, except the C sub 1 replaces 50. Thus, we have a C sub 1 in the objective function coefficient row and the C sub b column and the Z sub j and C sub j minus the Z sub j rows have been recomputed using the C sub 1 instead of 50. So, the current solution will remain optimal as long as the value of C sub 1 results in all C sub j less Z sub j is less than or equal to 0. So, here as you can see, wait a minute. Oops. That's it now. For the S sub 1, we have C1 less 64 over 5 is less than or equal to 0. So that is our S sub 1, and our S sub 3 is the 24 less C sub 1 over 5 is less than or equal to 0. So, using the first inequality, C sub 1, using the first inequality, we obtain C sub 1 less 64 is less than or equal to 0, or C sub 1 is less than or equal to 64. Then, for the second inequality, we have 24 less than or equal to C sub 1. So, because C sub 1 must satisfy both the both the inequalities, the range of optimality for C sub 1 is 24 is less than or equal to C sub 1, less than or equal to 64. So that's it. Let's proceed to next slide. So, to see how management of high-tech can make use of the sensitivity analysis information, suppose an increase in material costs reduces the profit contribution per unit for the Dash Pro to $30. So, the range optimality indicates that the current solution is optimal. So, as you can see, we have x sub 1 is equal to 30, x sub 2 is equal to 12, the s sub 1 is 0, s sub 2 is equal to 8, and the s sub 3 is 0. So, as what you can see, the optimal solution with c sub 1 is equal to 30 is the same as the optimal solution of c sub 1 is equal to 50. However, the decrease in the profit contribution per unit of the Dash Pro has caused a reduction in total profit of from $1,980 to $1,380. So, nagnubo ang ilang profit. So, proceed na sa next slide. So, what if the profit contribution per unit were reduced even further, say to $20, no? So, referring to the range of optimality for C sub 1 given by expression, we see that C sub 1 is equal to 20 is outside the range. Thus, we know that a change this large will cause a new basis to be optimal. To verify this new basis, we have modified the final simplex tableau by replacing C sub 1 by 20. So here, that is our table. So as expected, the current solution is no longer optimal because S sub 3 column of the net evaluation row is greater than 0. So this implies that at least one more simplex iterations in the previous tableau to optimal the new optimal solution will require the production of 16% units of dash pro and 20 units of portable. So, to illustrate the approach, we show the following final simplex tableau for the original high-tech problem after replacing 0, the objective function coefficient for S sub 1 with the coefficient C sub S sub 1. So, the produce that we use to compute C sub 1 can be used to any basic variable, while for the non-basic variable, it is easier because it causes only the corresponding C sub j less C sub j entry to change the final simplex tableau. So, as what you can see in our table, only changes are in the S sub 1. In applying inequality to compute the range of optimality, we get C sub S sub 1 is less than 14 over 5 is less than or equal to 0. As long as the objective function coefficient for S sub 1 is less than or equal to 14 over 5, it will be optimal. So, here are the steps to compute the range of optimality. So, step 1, or the first step, replace the numerical value of the objective function coefficient for x sub k with c sub k everywhere it appears in the final simplex tableau. So, the second step is recompute the c sub j less z sub j for each non-basic variable. If x sub k is a non-basic variable, it is only necessary to compute c sub k and z sub k. So the third step, requiring that c sub j less z sub j is less than or equal to 0, solve each inequality for any upper or lower bounds on c sub k. If two or more upper bounds are found for c sub k, the smallest of these is the upper bound on the optimal range of optimality. So, if two or more lower bounds are found, the largest of these is the lower bound on the range of optimality. The fourth step, if the original problem is minimization problem that was converted to a maximization problem, in order to apply the simplex method, multiply the inequalities obtained in step 3 by -1 and change the direction of the inequalities to obtain the ranges of optimality for the original minimization problem. So, by using the range of optimality to determine whether a change in objective function coefficient is large enough to cause a change in an optimal solution. So we can often avoid the process of formulating and solving a modified linear programming model. So next slide. So that is for the objective function coefficient. And now we will proceed to the right-hand side values. So, in many linear programming problems, we can interpret the right-hand side values as the resources available. For instance, in the high-tech industries problem, the right-hand side of constraint 1 represents the available assembly time. The right-hand side of constraint 2 represents the available portable display, and the right-hand side of constraint 3 represents the available warehouse space. So, dual prices provide information on the value of addition resources. In these cases, the ranges over which these dual prices are valid are given by the ranges for the right-hand side values. So, what is dual prices? So, we stated the improvement in the value of the optimal solution per unit. Increase in a constraint right-hand side value is called a dual price. So they are found in the C sub j row, the final simplex tableau. To illustrate this point, the final simplex tableau for the hydrogen is again shown. So this is our table. So in this table, we have 3 slack variable in the z sub j. So we have 14 over 5, 0, and 26 over 5. So we also have 14 over 5 equals to $2.80 as portable display constraint, and 26 over 5 is equal to $5.20 as warehouse capacity constraint. So the dual price of $5.20 shows that more warehouse space will have the biggest positive impact for the high-tech's profit. For the non-basic slack variables, in the previous slides, we have C sub S sub 1 is less than or equal to 14 over 5. It means that the S sub 1 should not increase to 0 unless it is worth more than 14 over 5 equals to $2.80. To do so, as a conclusion, $2.80 is the marginal value to high-techs of 1 hour of assembly time used in the production of Desk Pro and the portable computers. So next slide. So this is the tableau location of dual price by the constraint type. So we have less than or equal, and its dual price given by C sub j value for the slack variable associated with the constraint, less than or greater than or equal rather, negative of the Z sub j values for the surplus variable associated with the constraint, and equal is the C sub j value for the artificial variable associated with the constraint. So here, to illustrate the approach for computing dual prices for a minimization problem, recall the M&D chemicals problem that we solved in section 17.17, which is the previous chapter 17, as an equivalent maximization problem by multiplying the objective function by -1. The linear programming model for this problem and the final simplex tableau are restated as follows, with x sub 1 and x sub 2 representing the manufacturing quantities of products A and B respectively. So we have 2x sub 1 plus 3x sub 2, and 1x sub 1 greater than or equal to 125 is the demand for product A, and 1x sub 1 plus 1x sub 2 greater than or equal 350 is our total production. 2x sub 1 plus 1x sub 2 less than or equal 600 is our processing time. So, x sub 1 and x sub 2 is greater than or equal to 0. So, that is our table. So, the following rules in table of the tableau location of dual price by constraint type. So, that is here. Wait. So, that is the tableau location of dual price by constraint type. And here is the dual price constraint in the M&D chemicals problem. So that is the dual prices for M&D chemicals problem. So we have the constraint type, and the dual price. Excuse me. So for the explanation, constraint 1 is not binding and it's equal to 0. So the dual price for constraint 2 shows that the marginal cost of increasing the total production requirement is $4. No? Here $4. $4 per unit. Finally, the dual price of 1 for the third constraint show that the per unit of additional processing time is $1. So here, this is the range of feasibility. So as we have just seen, the C sub j row in the final simplex tableau can be used to determine the dual price and, as a result, predict the change in the value of the objective function corresponding to a unit change in a B sub I. This interpretation is only valid, however, as long as the change in B sub I is not large enough to make the current basic solution infeasible. Thus, we will be interested in calculating a range of values over which a particular B sub I can vary without any of the current basic variables becoming infeasible or less than 0. This range of values will be referred to as range of feasibility. So, to demonstrate the effect of changing a B sub I, we will increase the amount of assembly time from 150 to 160 hours. Given the dual price is $2.80 for the assembly time constraint, we can expect an increase in the value of the solution of 10 times 2.80 is equals to 28. So, as what you can see in our table, this is the final simplex tableau corresponding to an increase in the assembly time of 10 hours is shown here. So, the basic variables x sub 2, c sub 2, and x sub 1 is feasible because they are non-negative. Just as we predicted, the value of the optimal solution increased by 28 from 1980 to 2008. So, we have this for the new solution. So, here no, we have here the old solution. So, the change in B plus 10. So, here, the S sub 1, you'll just copy the S sub 1 column. Yeah? 8 over 25, negative 8 over 25, negative 5 over 25 over 14 over 5. It's the same as the new solution here. They are just the same. So this is the new solution. So again, we'll proceed to the next slide. So here in the table, so this is how we compute the upper and lower bounds for the maximum amount that B sub 1 can be changed before current optimal basis become infeasible. So here we have here we'll just copy. We will refer to the slide number 28. So we'll just copy the 12, 8, and 30 here. At here. Then the next one is the change in B sub 1, 8 over 25, negative 8 over 25, and negative 5 over 25. Let's just copy that. So here is the new solution. So using the solution in the previous slide, we satisfy the following condition. 12 plus 8 over 25, change in B sub 1 is greater than or equal to 0. 8 plus 8 over 25, change in B sub 1 is greater than or equal to 0. And 30 less 5 over 25, change in B sub 1 is greater than or equal to 0. So, solving for change in B sub 1 in inequalities, we obtain change in B sub 1 greater than or equal to 25 over 8 times negative 12 is equals to negative 37.5. Change in B sub 1 less than or equal to negative 25 over 8 times negative 8 is equal to 25. Change in B sub 1 less than or equal negative 25 over 5 times negative 30 is equal to 150. So here is the profit will increase to 1,980 plus the $2.80 times 25 is equal to $2,050. So the values of the optimal basic variable become x sub 2 is equal to 20, s sub 2 is equal to 0, and x sub 1 is equal to 25. Because the dual price for B sub 1 is 14 over 5, we know profit can be increased by 2.80 by obtaining addition how of assembly time. Suppose then that we increase B sub 1 by 25, that is, we increase B sub 1 to the upper limit of each range of infeasibility. As long as the change in a right hand side value is such that B sub 1 stays within its range of feasibility, the same basis will remain feasible and optimal. Changes force for B sub 1 outside its range of feasibility will force us to resolve the problem, to find a new optimal solution, consisting of a different set of basic variables. In any case, the calculation of the range of feasibility for each B sub 1 is valuable management information and should be included as part of the management report on any linear programming project. The range of visibility is typically made available as part of the computer solution to the problem. So, here is the last one is the simultaneous changes. So, in reviewing the procedure for developing the range of optimality and the range of visibility, we note that only one coefficient at a time was permitted to vary. Our statements concerning changes within these ranges were made with the understanding that no other coefficients are permitted to change. However, sometimes we can make the same statements when either two or more objective function coefficients or two or more right-hand sides are varied simultaneously. When the simultaneous changes satisfy the 100% rule, the same statements are applicable. So, for conclusion, sometimes interpreting dual prices and choosing the appropriate sign can be confusing. It often helps to think of this process as follows: relaxing a greater than or equal constraint means decreasing its right hand side, and relaxing a less than or equal constraint means increasing its right hand side. Relaxing a constraint permits improvement in value. Restricting a constraint has the opposite effect. In every case, the absolute value of the dual price gives the improvement in the optimal value associated the relaxing the constraint. So, in particular, recall that the 100% rule cannot be applied to simultaneous changes in the objective function and the right-hand sides. It applies only to simultaneous changes in one or the other. Also note that this rule does not mean that simultaneous changes that do not satisfy the rule will necessarily cause a change in the solution. For instance, any proportional change in all the objective function coefficients will leave the optimal solution unchanged, and any proportional change in all the right-hand sides will leave the dual price unchanged. So that's it for my topic. Thank you for listening.